diode as a semiconductor device. Now these devices, see, we know the applications, like we have already discussed how MOSFET can work as a switch, diode can work as a switch, how MOSFET can work as an amplifier. Am I audible to all of you? Please confirm via chat. Am I audible? Type Y in the chat box if I am audible to all of you. Dr. Geeta, can you hear me?
Yes, ma'am, I can hear you.
Thank you so much. Thank you. So basically, we have already discussed that how the diode can work like a switch, MOSFET can work like a switch on and off condition. It means logic applications, we can use MOSFET. And we can also discuss how the MOSFET can work like an amplifier, right? How we can prepare with the help of BJT or MOSFET, how we can prepare op-amp and related multiple operations. Based on that, we can do mathematical operations, filtering, integration, differentiation, and all. So now we are taking another application, which is a very good application, and this is very much effective also for research point of view. It is really good. So that is the electronic device sensors application. How the same device which you have actually gone through, how it will be working like in the digital logic circuit, analog logic circuit, and of course MOSFET device will also work like memory, right? For example, D flip-flop, etc. we can prepare with the help of MOSFET or BJT. So that is the application to the memory. Now the same device, let us take into consideration how it can work like a sensor. Yesterday's session, which was taken by the scientist from CSIR lab, that was very much effective. That was based on the MEMS sensors, right? So MEMS sensors will be taking into consideration the micro electromechanical systems. Like your device can be there, cannot be there, but during the fabrication, the MEMS fabrication is a little bit different. Now, today we are focusing on the theory part, how the sensors are prepared with the help of complete your MOSFET based, maybe tunnel FET based, diode based, etc. So these are the outlines for the day. Sensors, what are different kinds of sensors available in the market. Then the category of electronic sensors we will be choosing, and device as a sensor, diode sensor and MOSFET sensor, tunnel FET sensor, these will be taken. So these are the different types of sensors. Like you can have temperature sensor, chemical sensor, gyroscope, optical sensor, gas sensor, accelerometer, level sensor, proximity sensor, noise sensor, motion sensor, light sensor, etc. etc. So for example, let me give you a simple example. Earlier days, people used to have the transparent thermometer was used, which was having Hg, mercury inside it, and this mercury, which is assumed to be at liquid metal at room temperature, but it is very much poisonous also. So what we used to do is, it was kept into the mouth of the patient. So it was kept into the mouth of the patient under the tongue, and then there might be a change in the rise in the temperature. That reading was actually recorded, and that's what, let's see, it is 97 degree Fahrenheit. So that reading was recorded, and that's what you actually used to have, that what is your temperature. After that, in the market we came to know the electronic sensors. So how the electronic sensors will be working? The electronic sensors will be sensing. You will be put in the body part which are having like constant temperature according to your body. So maybe under the armpit, or maybe somewhere similar kind of thing, somewhere other place you will be putting that, and then the temperature sensor, which was electronic, the temperature was rising, and the recording was actually displayed on your display panel, right? So display panel was digital. There was just need to read the reading, and your job is done. Then thanks to Corona, the new innovation came, that this is your forehead, and you will be putting the sensor in front of this, and that was the infrared sensor, IR sensor, IR light sensor. So these were the different innovations have happened for the temperature sensing, the body temperature is specifically sensing. These are the applications. So see, there are multiple types of temperature sensing. Body temperature is having a set pattern. Like you can have maybe 95 degree Fahrenheit to 105 degree Fahrenheit. This is the typical range you can have. So it means it can work in this range, but for space applications and all, different kinds of temperature sensors are needed. So for that, we have to think that what is the application for a particular sensing application we are talking about, and we will take that accordingly. Okay. So basically, sensors are working on some phenomena. What is that phenomena? For example, uh, chemical sensors. Ion sensors are there. Ion sensors are chemical sensors. These chemical sensors can be humidity sensor. That humidity sensor can be of three categories: resistance sensor, capacitance sensor, and other sensors. So when we are coming to resistor and capacitor or maybe inductor, it means we are coming to the electrical characteristics, current and voltage. If somehow my sensing could happen in the change of resistance or capacitance, it means I am going towards the IV characteristics, and IV characteristics means it is electrical engineering. So I will be having the I will be noticing the change on the pro rata basis, and that change is calibrated against the real change in whatever parameter you will be having. For example, humidity. Likewise, chemical sensor can be gas sensor and biosensor. So gas sensor can be semiconductor gas sensor, electrochemical gas sensor, contact combustion gas sensor, polymer gas sensor, optical gas sensor, etc. etc. So we can have the category according to our branch, we can have the category of semiconductor gas sensor. How it is going to work? So gas is being bombarded at some surface. That surface parametrics will get changed, and that change in that surface parametrics will be actually seen as your device characteristics. Likewise, you can have biosensors. So in biosensor, you can have microbial biosensor, enzyme sensor, immunosensor, etc. etc. So these are the different types of sensors, and yeah, in ion category, you can have ion selective fats and solid film ion sensors. These are the categories. So first of all, let us take the light detector. Light detector means some light with some particular intensity is coming, and you want to detect whether this light is with this particular intensity, or intensity is going to increase or decrease. For example, we are talking about solar cell. So what is the principle of solar cell? If somewhere you have seen there is a pumping motor, in many of the places you have the pumping motor. This pumping motor based on solar cell works really good if the temperature is not too high. Means in the winter season also, only just the temperature is there, only simple very minimal temperature is there, then also this is going to work really high. Okay, this is the water. It is not light. I have given the symbol of light. Yeah, this is water. So this pumping water means it requires much more horsepower is required for the motor, pumping motor, and then still it is going to work well. So it means what? It means it is the light intensity which really matters. Light intensity. Remember, it is light intensity, not the external temperature. So the light intensity when you are letting fall at the PIN junction, basically the solar cell is made up of multiple PIN junction diodes. Okay, so solar cell is kind of a light detector only. It is going to detect the light, and you can say it is a photosensor. It is a photosensor. The best example of photosensor, commercial example, is nothing but your solar cell. Okay, now how this solar cell is made up of? Solar cell is made up of N-type and P-type material. In between, sometimes you can actually have I rays. I is the intrinsic. Okay, so basically you can see this is PIN structure. Let's say it is P, then let's say it is I, and then let's say it is N. Now you have to put your contact over here and you have to put your contact over here. And if both of these are being connected, you will be getting, if you want to find out some voltage across these 2 points, that is the open circuit voltage. If you want to see the current through it, that is known as the short circuit current. So these are the characteristics which are open circuit voltage and the short circuit current are the characteristics in case of solar cell, which are going to tell you that how your MOSFET, a solar cell gives the power, how much power it can give. So basically what is going to happen is you are letting fall your light over here. This is the PIN junction. So the photons are actually let fall at the intrinsic region. Intrinsic region is actually widening our depletion region. In the PN junction diode, we know that it is going to widen our depletion region. So intrinsic region, if you are putting, that is expected to be having very less amount of KVL, so it is getting widened. So basically there is no current flow. And solar cell or the photodiodes will be working in the reverse bias. If these are going to work in the reverse bias, then again there is a problem. In the reverse bias, this particular distance is getting widened more. So if you are letting photons to fall on this junction, this particular junction, what is going to happen? Electron hole pairs are being generated in the I layer, which is the intrinsic layer. In the intrinsic layer, electron hole pairs are being generated. These electron hole pairs, if you are connecting this to a battery in the reverse bias, the electron hole pairs are being generated and these electrons actually go towards this way and the holes will move towards this way. So because of that, the current flow is seen in the PIN junction, reverse bias PIN junction, or the PN junction we can say. So how it is made up of? See, we know, okay, that this is a reverse bias PN junction, but how I will be making sure that my light is falling at this particular portion only? Because I will be making it like, either I can make it in this way, okay, this is my N junction, N type, this is my I type, and this is my P type. And I am expected to let the light fall over here. So how I can prepare that? That is really very difficult task. So how we have to do practically? First of all, there is a material called as ITO. ITO is a compound conductor. ITO is known as indium tin oxide. Indium tin oxide is a transparent conductor. This transparent conductor lets light fall into it. The light is let fall to this particular junction, this particular semiconductor. This particular semiconductor is having very small thickness, small enough, let's say it is having around 100 nanometer. So 100 nanometer means it is the thickness of my hair, right? Yeah, it is even lesser than the thickness of my hair. It means this particular light can pass through this region and it can come to this region. Once it is going to come into this region, which was the I region, electron hole pairs are being generated. Electron hole pairs are being generated. Why electron hole pairs are being generated? Because we know that the silicon intrinsic means it is a pure semiconductor, right? So the silicon at 0-degree temperature works like the fully filled states. All states are fully filled. This is your silicon. So everywhere the bond is prepared. This way also silicon, silicon this way, silicon this way. So at absolute zero temperature, what is going to happen? These covalent bonds are being occupied. So there is no free charge carrier. As you are increasing the temperature, what is going to happen? Increase in the temperature is leading to give the energy to these electrons, the covalent bonds, and these electrons will get excited and will come out of their state, leaving behind the hole, and the electron is moving in the material space. So basically the electron hole pair is being generated and this is called as the generation, electron hole pair generation. And the reverse of this, when the electron is losing its energy and settling down into any of the covalent bonds, that is known as the, what do we call that? Recombination process, right? That is known as the electron hole pair recombination process. Means both of the pairs are getting recombined and the energy is being released, right? So here the light is coming to this junction in this way, which is we have shown in this diagram in particular way, and then the electron hole pairs are being generated, and then you can see the current characteristics are being changed. Now the similar thing you can utilize with this is actually nothing but BJT. In BJT you have NPN junction. This is N, then P, and then N junction. So in this NPN transistor, you will be focusing on the reverse bias junction. The light is focused on the reverse bias junction, and then it will get modulated. So whatever the reverse bias current IB will be there, the IC current is beta times of that. So the total current in the photo transistor is more as compared to the photodiode, because whatever reverse bias current will be seen, reverse bias current is nothing but the reverse saturation current of the diode. So if you remember, you can recall the diode characteristics. In the forward bias, it was on after a particular threshold, right? And in the reverse bias, it was getting low. So this was on in the forward bias. In the reverse bias, if let's say I have taken this milliamps and I am going to take it nanoamps. Look at the scale, I have taken it nanoamps. So this was your VD and this axis is your ID. So in nanoamps, this will look in this way. It is going to look in this way, right? Because since it is nanoampere, so it is actually, if you will make it milliamps or microamps, it is very near to x-axis. I am changing the pen to just show you. So it will look like this if you are taking it microamps. So these are the diode IV characteristics. We are using in the reverse bias, means this is the quadrant, and this is what? This is nothing but the reverse saturation current, and this reverse saturation current is basically getting increased if you are going to make photons let fall at the intrinsic junction, intrinsic region, and this amount of current is getting modulated. This IS current is getting modulated. So the same has been shown in this particular diagram, that how it is getting changed. Basically, it is going to tell in terms of capacitance, that in terms of current can be seen. So this current is more the number of carriers are being generated, this current characteristics you will get in this way. So you can see more the intensity, the current is getting increased in this way. The current is getting increased in this way. So in this manner, the current in the photodiode is getting increased. That is we can calibrate that reverse bias saturation current against the light intensity, and in this fashion we can get the light intensity or the sensitivity curve. Okay, so basically from third quadrant, if you are bringing into first quadrant, let's say you are putting it reverse bias. So this is going to happen in this way. The intensity of this is being increased. So this is the reverse bias saturation current is getting increased. Yeah, according to the intensity of the light. So this was your diode reverse bias, and this was your current. Of course, in the negative direction, you will be having the current. So these will be the IV characteristics of your photodiode. Phototransistor will also be having the similar characteristics, because there also the reverse bias is taken at the junction and then it is prepared. Now next one is MOSFET working principle. First let us revise the MOSFET working principle so that we can utilize MOSFET as a simple sensor. So in this case, I have taken N channel MOSFET. This is N plus region, and this is the channel region. These are the IV characteristics, only the output characteristics I have taken over here. So this is the cutoff region when VTH is less than, VGS is less than VTH, and this is the ohmic region or linear region. Linear region because it is kind of a straight line, right? So in this particular region, it is a kind of a straight line. and this straight line, because V is proportional to I, and because of that, or let's say I is proportional to V, so because of that we call that this is the equation of line is being followed, and that's what we call this as ohmic region or the linear region. And this particular region is the active region or the saturation region. So in case of MOSFET, we call this as saturation region. Instead of active region, we will be calling that this is the saturation region. Okay. So now what we are going to do, we are going to play with some of its physical parameters or materials, so that we can convert this into a sensor. For example, let me take one example, pH sensor. pH sensor, for example, pH sensor is having the scale starting from, where is the neutral for the pH? 7, right? If you are moving away from it, if you are moving towards base to acid. So it tells you the nature, that what type of material, what type of that particular thing you have. So it might be basic nature, or it might be acidic in nature. So it means the pH sensor is going to give you many of the applications. I will discuss one or two applications related to it, so that that can be put for thought for your research. Okay. Yes. So in pH sensor, this is actually the liquid solution. You want to find out what is the pH of this. Let's say you want to find out what is the pH of your blood. So what you have to do, you have to take the blood sample, you have to put your reference electrode over here, and then you have to put the other electrode which is connected to the device. So this reference electrode is getting connected. This is the reference electrode. It is getting connected to this VG reference. Right? This is connected to the VG reference, and this is actually the electrode which is connected to the device. So there are two electrodes. Basically, you are going to apply this VGG voltage. You are going to apply this VGG voltage to this particular MOSFET. This is the VGG voltage. You are expecting to apply this voltage over here, but instead of directly putting your wire, what you did is you actually applied it through this channel, and then this is the liquid. Because liquid is conductive, it is having ions, so it means through this you are going to apply it in this way. So now if you are applying some voltage in a particular liquid, so because of its ions, what is going to happen, its characteristics are being changed. Let's say some resistance is being offered by it, and that resistance will see some drop across it, and that drop actually is reducing this particular VGS applied over here, and because of that your characteristics are being modulated, and those characteristics you will be recording, and those change in the characteristics is equivalently calibrated to find out that what was your pH sense, what was your pH level, what was your pH level, you can sense it in that way. Now the thing is, many times what is going to happen, since your MOSFET device is very small device, you are working in nano meters area, let's say 180 nanometer technology node is the stable one in India. SCL Chandigarh can fabricate that for you, and there are a few charges only for that, right? SCL Chandigarh is one of the government unit which is going to offer you the fabrication of these devices. Others are through INUP. INUP is a program through which you can get your devices fabricated from ISC Bangalore and IIT Bombay, right? So nowadays, few of the fabrication facilities are also there in IIT Delhi also. So you need to explore, and for this, it is free of cost for the researchers and faculty members. So you have to work, and then you have to bring out the publications, then you have to give your whatever you have designed with all those things. You have to give it to that, what type of material you are going to use, what are the sizes and all. You have to give the circuit to the through INUP. It is like the project proposal will be open. You have to give your project proposal, you have to submit, and then they will be calling you. So everything is free of cost. Your stay over there, IIT Bombay or ISC Bangalore, they will be making your device for you, and then you can test it. So if you do not have testing facility also, you can utilize those labs, maybe IIT Bombay, ISC Bangalore, or somewhere else you can utilize. Some of the facilities also are here in MNIT Jaipur in Material Research Center, like for probe method, to for the measurement and related things, and a little bit of fabrication facilities also we have at MNIT Jaipur. So you can utilize those facilities on payment basis. It is there. Yes, and the charges are very much nominal. I think 250 rupees charges for per sample or something they are charged. So actually how to prepare this, because the device is going to be very small, right? I do not know that where is its contact, right? So if I do not know that, it is difficult for me to arrange and connect it, the electrode to this beaker, right? It's difficult. So how the researchers are going to prepare it? The researchers are going to prepare the MOSFET in the simpler way. Then they are putting the blocking as insulation layer. This insulation layer is not going to react with this material, whatever the liquid material, to figure out what is the pH level of this. You want to take the sample. This is made sure that this, whatever this material you have taken, that is insulating for this, it is not going to react chemically. Not only electrical insulation, but it is chemical insulation also for this particular electrolyte. Now your reference electrode is put inside this electrode, and some VCC supply is given over here. Now how these things are being changed, how they see the drain current will be seen. You will be applying the drain current will be seen. This is, yeah, some drain voltage is there, and this is how. So whatever is changed there in the drain current, that is noted, and this is how that is calibrated against how much pH level was there, how it is done. So look at this. Here we are going to apply VGG, right? We are going to apply VGG. Okay, some drop is seen across this. Some drop is seen across this because there is ionic movement, and because of that there is, if it is not resistive, it can be capacitive. Like we know that Q is equal to CV. Ions are moving here and there. There is particular, when ions are going to move, some voltage drop is seen. So charging and discharging of these electrons can take place, just like in your electrolyte battery. So because of that, in some materials it is resistive also. In some materials it is resistive also. In this case it is capacitive, I believe. So what is going to happen? This change in the voltage, let's say some of the voltage is dropped, and here you are going to look into VGS dash instead of VGG. So what we know about the equation for the MOSFET, IDS can be taken up as mu NC x W by L into VGS minus VT. And let's say I'm going to take VDS good enough. Okay, if you want to take VDS good enough, it means you were expecting that there will be saturation, right? You are having VDS. VDS is, let's say, you have taken VGS minus VT. So since VGS is decreasing to VGG, so you can take it VGG minus, greater than VGG minus VT, so that you can make it sure that the system is in saturation. So if the system is already in saturation, this VDS is fixed, right? It's been fixed. VGG is also fixed. but Vg dash, Vgs is equal to Vgg dash, means some drop from the reference potential to some drop from this is the reference electrode to the surface of this insulator, because the surface of insulator is going to work like a gate electrode, right? So whatever the change is seen, that actually whatever you will be seeing over here at the surface, that VGS is actually controlling your current in the device. So the current is being controlled by the device through this VGG dash, that is nothing but VGS, right? Now if this is changing, VGS is changing, your current is being changing. You can see at the IV characteristics. So these are the output IV characteristics. So these were the IV characteristics. Since we have done it in the saturation mode, so it means you are going to get higher amount of current according to how much your VGS is getting changed or not. So if VGS is getting increased, this is the lowest VGS value, and then it is going to increase in this way. Let's say VGS 4, and it is increasing in this way, and that is going to increase the current. So VDS was fixed, so it means you are somewhere at some place, okay, and this is ID. You can get the full characteristics also. Since you are just changing your VDS, so you will be getting one particular curve, and then with the help of more electrolyte, more pH, you will be getting maybe second curve, and that curve is going to tell that okay, that was the pH level has been changed of that particular electrolyte. So this is the pH sensing. If you have any question in this, you may type in the chat box. Otherwise, we can take the next sensor. Do you have any questions so far? Type N in the chat box if you do not have any question. Yes, please. No questions. Okay. So let me take the next one, the force sensor. So MOSFET force sensor. What is force? Force is you are trying to press it. You are putting the force over here. It means this is per unit area. It is a pressure, right? Force per unit area is pressure. So you are pressurizing it. If you are pressurizing it, there was yesterday we have gone through like pressure sensor. In MEMS category, we have gone through the pressure sensor. So yesterday such type of pressure sensor you have done, right? This was the membrane, and the pressure, maybe the voice signal or something is bombarding over here, and because of that there was a deflection, and because of that resistive or some other parameter is going to change. Electrical parameters of this membrane was getting changed, and because of that change, let's say delta R is being changed. Because of that change, there was a change in the Wheatstone bridge output voltage, and that voltage was recorded, and that's how that is calibrated against whatever the pressure was applied. So that was the pressure sensor. So pressure is nothing but force, right? That's the force only. So that we have taken from MEMS perspective, and the same thing we are going to take from this MOSFET perspective. So let us consider how it is going to work. So it is the force. We are going to apply this force over here. We know there is something piezoelectric material. Piezoelectric material. What is that? Piezoelectric materials are actually, when you are going to apply some force, so it is going to change its electrical characteristics. Its resistance, its dimensions are being modulated, and some voltage is being developed. Or if you are going to apply some voltage, then the deformation in its size is going to happen, right? So you are going to apply some force, so it means the size is being deformed, right? So initially, let's say it was like this. We are talking about this particular area. So this particular area after the pressure, let's see, I am going to change the color. It is deformed in this way. So after force or pressure, it is being deformed in this way. If it is being deformed, it means you can see over here the thickness between these two terminals has been changed. If the thickness of these two terminals has been changed, can I say that the effective capacitance has been changed? Because what is CUX? CUX is the capacitance per unit area epsilon ox upon T ox. If the thickness is being modulated, it means the capacitance is also being modulated. And what we know about the current equation, so here this current is directly proportional to your COX, right? So it means the current is being modulated. You will keep your VGS and VDS constant and you will find out how your IDS is being changed. So depending on that, of course, it will be a function of COX only. So if COX is increasing and other things are constant, there will be a linear behavior of the current and the COX applied. And the COX and force, how these are having the behavior, that will be decided by the piezoelectric material. So from these two properties, we can figure out that what was the force applied over here or the pressure applied over here. So this is how the MOSFET can work like a force sensor or pressure sensor. Any confusion so far? If you have any confusion, we can take the question. Otherwise, let us proceed further. No questions? Okay. Now the same thing, let us understand how the image sensor works. So MOSFET has an image sensor. So what is image? So let's suppose you are letting light fall to this particular section that is black, and let's say adjacent to it there is another section which is white, and adjacent to both of these there is another section which is red. So I am letting my light fall to this one, and this one. So what I know about it, see, when we are taking some image, for example, nowadays there is digital camera, 2 megapixel, 4 megapixel, like that you have the digital camera, 48 megapixel, 64 megapixel. These are the categories of the digital cameras. In these digital cameras, one picture is converted into those many pixels, right? And one pixel is corresponding to 3 sensors, and these sensors are red, green and blue. 3 sensors. Why these 3 colors are being taken? These 3 colors are being taken because these 3 colors combining all together, can you give me any kind of color combination can be taken up with the help of these. So because of that, we'll be taking these 3 colors all together. Okay. Yes. Am I audible to all of you? Not audible. So Dr. Geeta, can you hear me? Dr. Geeta, can you hear me?
Yes, ma'am. Yes, ma'am.
Oh, okay. So I am looking that there are 53 participants on my other app. So please take care while marking the attendance, because in browser view less number of attendants are seen, but in the app I think all of them are seen.
Okay.
So please count the attendance accordingly so that we are not going to miss out any of the candidates.
Sure. Okay.
Okay, thank you so much. Yeah. So let's come back to the topic. So this is the RGB color. With the help of RGB color, what you can do is you can make any color. For example, I want to take white color. So white color is what I will be making. This is RGB. So white color means what I have to do. I have to take all of these R, G and B, 1, 1, 1. If you want to have a black color, so black color means all of these you will be setting to 0, 0, 0. Now from this to this is the journey that different colors will be seen. For example, I want to have a blue color. So for blue color, you can have maybe, you can, I think here, when you will be combining green and black, you will be getting blue. Likewise, R and G, if connected together, yellow. I'm not sure, you please just check it. So this is like how the colors are being prepared. Only 3 colors are required. So for each color, you need a sensor. One image sensor is needed. And that image sensor is nothing but your basic sensing device. Okay. So now let us consider out of this 48 pixels, 1 pixel you will be taking. Out of that 1 pixel, any one of them you will be taking, and this device is actually that sensing element. Okay. Now how it is going to work? So it is going to work in this way. So let me draw the another circuit. Let me take the blank slide and then I'll be explaining that. So basically, this is your MOSFET, right? So in your MOSFET, I have drawn N plus region, which is nothing but source and drain. This is, let's say, drain side. This is your source side. This is your P type substrate or body contact, right? Now, let me take my oxide from this to this, and this is my metallic gate. And here, yeah, I'm going to put my gate. This is my source connection, and this is my drain connection. I have left this particular region as it is. Okay. Now what is going to happen if I am going to increase my VGS? So it means, let me change the color. If I am going to increase my VGS, it means number of electrons will get accumulated over here. Can you visualize this sky blue color on the screen? This is just to show that the electrons are coming over here, right? Type Y in the chat box if you can see this. Yes? You can't see or you can't hear? Okay, fine. So now VGS, if you are increasing, so it means you are increasing the carrier in this channel and this channel is formed. If you are increasing VDS, so VDS means from this to this was your LG, the gate length. And now the channel actually is being formed from here to here. The layer of electrons is there. So increasing the number of electrons means the resistivity is decreased, right? And the conductivity, if you remember, NQ mu, that's been increased. Resistivity is decreased and the conductivity has been increased. So from here to here, the resistivity is decreased. But what about this? Because still here, there are no carriers. It is intrinsic kind of only. So if you talk about NQ mu over here, this is negligibly small. The conductivity stops over here. So it means what we are going to do, we are going to put the light intensity according to the color over here. So how the image sensor works, the image sensor will be working. First of all, you will be taking a light source. This light source is let fall on your image. Now, how much your eyes are going to detect out of it, that is nothing but your color sensing mechanism. Basic principle you might have studied in your 10th standard or maybe 9th standard, like that. So this is the light source. This is your image. On this image, you are letting the light fall. After this, depending on the color, it is reflecting some of the light, and that reflected light actually is sensed, and that's what the color sensing mechanism is going to work. So our eyes are also color sensors kind of. So this particular light, let me give it reflected light. So this is nothing but here it is reflected light. Okay. Now this light is let fall over here. This is going to modulate electron hole pairs are being generated just like your simple photo diode or something like that. So that is going to create the electron hole pair that is going to increase its mobility and decreasing the increasing the conductivity and decreasing the resistivity. If the resistivity is decreased, then the current is getting increased because this VDF is being applied between these two terminals. So this can be considered in this way, that there was some resistance offered by the gate or let's say channel, and there was other window which was open, so that resistance was this resistance because of the image sensor, that was the underlapped region. So whatever light you will be falling over here, that was nothing but the reflected light depending on the color. For example, we know if the color is black, then the complete light it is absorbed. If the color is white, the maximum light is actually reflected. If the color is somewhere intermediate, Vibgyor is the formula, right? If that's the pattern, it means correspondingly your light intensity is getting changed depending on the color. And we will utilize that formula, that what is the wavelength of the light. Depending on that wavelength of the light, we are going to give you the energy. There is the energy packet h nu, right, of those light packets, photons. So that h nu energy is going to create the electron hole pairs. Those electron hole pairs are going to contribute to the conductivity, or maybe they are making the resistivity down, right? And that's how the current through this is seen more. The current is seen more or less. So with the help of this, we can actually work MOSFET. We can utilize MOSFET as an image sensor. Okay. Any confusion so far? If you have any confusion, please feel free to ask in chat box. Otherwise, let me take the next one. So the next one is the tunnel fat as biosensor. So whatever we have discussed till now, we have discussed image sensor, we have discussed pH sensor in the electrolyte, right? And what else we discussed? Photo sensor we have discussed, light sensor we have discussed. Light sensor and image sensor, these are similar, because in image sensor also basically we are going to detect the light, but in the light sensor we are going to take the direct light, but in image sensor we are going to collect the reflected light, and that light we are letting fall at the required area, okay, which was open specifically for the light sensing mechanism. That area we need to keep open so that the light can fall over there easily. So how to prepare that? Because if you are going to make that open, if you are going to make this particular thing open forever, then there is the problem that the charge is, if you are going to make this particular region open, what is going to happen, that there is the possibility that there can be some doping because of the environmental issues can be possible, or your device because of the temperature, humidity and other parameters are directly sensed by this environment, which is the semiconductor, which is very sensitive. So it is not going to work in a good way. So what you have to do is you have to make sure that a very thin film of a transparent material is layered on the top of this particular opening, so that the light can pass through that particular material and it can actually contribute to the electron hole pair generation to the wanted area. So this type of thing can be done with the help of uh, you know transparent kind of material, putting the transparent kind of material over here, and the material should also let pass the light. Those should be transparent for the light, especially those type of materials can be layered, right? For example, if you talk about graphene, Graphene is completely transparent material. It actually gives no 100% transmission of the light. It will not absorb anything. This is transparent by the color also, from the light phenomena also, that's the transparent. Yes. So now let's come to the tunnel fat. We'll take 5-7 more minutes since we started a little late. So 5-7 more minutes will be taken. So now let's take the category of biosensors. Biosensors are actually many of the people are working in biosensors, finding out the real-time applications, and engineers are helping to medical industry with the help of biosensor and its applications to the various domains. So basically, whatever sensors we'll be utilizing, those will be working on the principle that the electrical characteristics are being changed. Electrical characteristics are being modulated. So that is possible with the help of either resistance is being changed, or maybe capacitance, or maybe inductance. So inductance is not there in the picture. Only resistance and capacitance will be focusing on these two parameters actually are being changed, and because of that the current is being modulated. So that we will focus on, right? So biosensors are of two types. One of my research scholar, Dr. Basudha Devan, has worked on tunnel fed based biosensors. So I have taken these slides related to biosensors from her work. Fine. So there are two types of biosensors. One is labeled and label free. Labeled and label free biosensors. What is the meaning of labeled? Oh, so so am I audible? Am I audible? Am I audible? Am I audible? Not audible?
Yes, ma'am, audible. You are audible.
Okay. Yeah, I was just checking that everything is going fine. So because of that, the another device speaker was also on. Yes. So basically, biosensors are labeled and label free. Labeled means you are having the antigens. These are the antigens, and these are the primary antibodies. These are the secondary antibodies. In case of labeled, what you are going to do is you are going to detect this antigen with the help of antibodies putting on the top of it. One primary antibody and secondary antibody, both of these are taking antigen all together in order to chemically react on that. Another is label free. In label free, only one primary antibody is required and your antigen is sitting on the top, and then whatever chemical reaction is there, depending on that, there is some phenomena is going to happen, and that's what your job is done. So that's what the label free and labeled biosensors are there. So we'll be talking about label free, means no extra secondary antibody is required, and we will just taking the antigen and then we will be detecting. So how it works, the schematic block diagram of the biosensing system is given over here. First of all, there is analyte, and then the analyte is given to the bioreceptor. Bioreceptor can be enzyme, cell, DNA, nanoparticles, or something like that. Then this information for biorecognition, it is given to the transducer. This information can be maybe light, heat, mass change, pH change, or something that is given to the transducer. So transducer can be, for example, if it is light, you may giving this to the photodiode. If it is heat, you will be giving that to the thermistor. Yesterday it was discussed, I believe, in the MEMS category. pH sensor, for pH electrode you will be giving. Mass change for quartz electrode you will be giving. And now this is going to produce some signal. That signal is going to give you to your A to D converter, analog to digital converter, and then it is going to come to your display that what actually the thing is going to happen. This is the schematic block diagram. Now let us understand the tunnel fat working, because we are using the tunnel fat as a biosensor. So if you remember, if you can recall, the tunnel fat was having source and drain which were of different doping. So this region was P plus region, which was source, then the gate region, and then the drain region, which was N plus region, drain. And the gate was intrinsic region. You remember? Then here there was gate oxide, and on the top of that there was metallic layer. So source, drain, and gate, these are the three things over here. So since source is P type, so in the steady state conditions, as I told you yesterday, that the source is degenerately doped, this will be your steady state without giving any input to the drain. So the drain is near to, this is a Fermi level, so across all the materials your Fermi level is aligned. This was degenerately doped, so because it was degenerately doped, so your EF is inside your valence band. This was intrinsic but towards a little bit P type, so I have taken it upside, but it will be a little bit downside, middle and little bit downside, and this is near to the conduction band. If you are going to apply some drain voltage, it is coming down and you'll be getting this blue color, whatever it is there. So still you can see the electron cannot cross this barrier. If you are increasing your gate voltage, then this electron is crossing this barrier, and this is how the current flow is going to happen. If you are decreasing this voltage, so the energy band diagrams are going upside. So in this case also there is actually the conduction of electrons is going to happen through this. So this is known as the ambipolar state. Ambipolar means, ambi means both the ways. So the current is flowing in this way, the positive side of the gate voltage also and negative side of the gate voltage also, that will be calling as ambipolar behavior of the device. Now with this knowledge, let us proceed to work the tunnel FET device just like a sensor. So in this diagram, it is shown that how the tunnel FET can work like a sensor. Over here, you can see that this is your source, which is made up of, this is your source, induced source, P plus region, silicon germanium we have taken. This is the original work Dr. Basudha Devan has submitted for her PhD thesis. Then there is intrinsic channel, which is made up of silicon. So we have taken it heterojunction. This is silicon germanium and it is silicon. And then this is also silicon. So this heterojunction has been taken over here because of certain increment in the current was seen because of this, and that's what we have taken this heterojunction. Then look at this, these are the terminals for source, and this is for the source and this is for the drain, right? So the work function is shown over here for these particular materials, and here you can see we were expected to have a layer of oxide over here. So what we were expected to have, we were expected that this should go in this way. This is your source, P plus region, and this is your drain, N plus region. You were expected to have the gate oxide over here, and you were expected to have your gate contact over here. This is your gate contact, and then source and the drain. So this is the gate contact, this is your drain, and this is what your source is, right? So here you were expected to have the oxide layer. What we did, we have modulated this oxide layer. How we modulated it? This is your SiO2 layer, this thin surface you can see, this is your oxide layer. Let me change the color. I hope this will be fine. So this is just over here, this is your SiO2 layer. What is this? SiO2 layer. Next to it, it is HFO2. This, from this to this, which is HFO2. HFO2 is also one of the oxide. Okay, but that is having high K side. Now, what is here? This was actually a cavity. You can see the red particles are there. These are nothing but biomolecules in the nanocavity. So we have to make this cavity. This is the cavity. You can see the red pointer. I think it is visualized on your screen. So this is cavity. In this cavity, there are biomolecules placed. So we have to inject the biomolecules over here. So for example, if you want to check something, uh, you can take, let's say from blood you want to check something. So take the blood plasma and put the blood plasma in this cavity. Now this cavity is filled with the blood plasma. So there will be biomolecules which you are going to detect, plus some more molecules which are not going to affect anything, but those will be filled in this cavity, right? Now these biomolecules will be having certain electrical characteristics. What kind of electrical characteristics? For example, it can be positively charged, it can be negatively charged, it can be charged neutral, and it can also have some electric permittivity. So that electric permittivity we need for this was the insulate, right? So here, if let's say this was having some electrical permittivity and it is charge neutral. So if it is charge neutral, then this whole is working just like your oxide layer. Okay, this complete was working just like your oxide layer. So can I think of that this is one type of the epsilon 1 and the next one is epsilon 2. So there will be two capacitances in series. There will be, for this particular reason, there will be two capacitances seen in series. One is because of the biomolecules and other one is because of the SiO2 layer. That is parallel with HFO2, which is having the same, some capacitances offered by that. So depending on this, let me give the name C-bio to this, CSiO2 to this, and this is CHFO2. Okay, so the equivalent oxide COX will be a combination of all these capacitances, and this actually effectively is going to create the band-to-band tunneling, because the band structure, the band energy band diagrams were actually modulated with the help of the gate, which was actually taken into consideration through this COX. The energy band diagrams were somewhat like this. In the normal conditions, it was somewhat like this. So this is being modulated if you are having biomolecule is having the particular category. So that will be having the particular epsilon, that will be having the particular number of ions, positively charged, negatively charged, or maybe charge neutrality condition might be there. And depending on that, this is being modulated and the current IV characteristics are also being modulated. Okay. So we will be studying that IV characteristics. Based on that IV characteristics, we will be finding out the sensitivity for this particular device, and that actually completes our study. So sensitivity, there is three types of sensitivity we have taken into consideration. We have taken the drain current sensitivity into consideration in this particular thing. Another category is ion by IO ratio and IO ratio alone. That these are the different categories of VTH. Okay, VTH is also one of the parameter to sense it. So here only the on current sensitivity is taken into consideration. This is given by this particular formula. S ion is equal to I on, which is nothing but the drain current with the biomolecule field, minus when there was no biomolecule field, that is air, divided by I on air. So this was the drain current sensitivity analysis, and with the help of K is nothing but the relative permittivity constant. So K is equal to 2, 6, 10, 12, these are taken, and you can see for every one of these we are getting a different curve. That different curve is going to signify, and these all are because of different charged biomolecules, positive and negative charged biomolecules, positive charged biomolecules, and like that. Okay, so that is going to give us the is that how uh, the device you have prepared can sense the biomolecules, and this is working like a biosensor. So if you have any questions, please feel free to ask. Type in the chat box and we can quickly have 1 minute question answer session, and then let us close the session for the day. We'll be meeting at 3 p.m. in the evening, and then we'll be discussing hands-on related to whatever we have discussed now. So I have shared you one video link. If you can install the Silvaco, maybe I will be sharing shortly the related files of Silvaco. You can just try to install that, and if you can work all together, it will be helpful for you. Otherwise, what you can do later on, you can do the practice with the help of the video will be sharing. Recorded videos are shared, right? So you can work with the help of this, and will be helping you. You can get back to me. Definitely, I will revert back and help. So this software you can also have in your labs. You can work over there. Okay, thank you so much. If you have any queries, please feel free to type in the chat box, or we can also take that query related to this.